All right, this is the 5.4 section notes. There was one word problem we didn't do together in class today. So I wanted to make sure I had that on this video. And then there were, I had most of the problems that we didn't do from 5.5 and 5.6 on a pre-recorded video that I already posted, but I wanted to go back and fill in all of the ones that were missing. So that's also going to be included in this video. So for 5.4, it says if interest is compounded continuously, so notice that's really important to helping us pick the correct formula. We use the one with the E in it for compound interest when we're doing continuously. And it said our rate is 6% per year, so that'd be 0.06. We want to approximate the number of years, so we don't know time. That will take an initial deposit, so that's our P, of 6,000 to grow to 25,000. So we want our future value to be that 25,000. Okay, so we're going to plug in everything we know and try to solve for what's missing. So we have 25,000 equals 6,000 e to the 0.06t. So anytime you're trying to solve for an exponent, you want to, first of all, make sure that the base connected to that exponent is isolated. That's always kind of our first step to check. So we're going to divide that 6,000 over. And that will then, those zeros right there will cancel out. That'll be 25 over 6 if we reduce that down. Now, unfortunately, 25 over 6 and e are definitely not the same base. So when we get to a problem where we have a single variable and an exponent, and we're trying to solve for it, and our bases don't match, we can convert this to log form. So remember, log is a base, an argument, and on the other side was the exponent. So e is the base, 0.06t is the exponent, so that's going to go on the other side. The leftover part that we haven't used is our argument, so 25 over 6. Now remember, we talked about in class today that log E is not necessarily how we write that. That is shorthanded as ln, or natural log. So log 25 over 6, so natural log, equals 0.06t. And now t is no longer in an exponent because we converted to log form. So we're able to solve this by dividing by the 0.06. So this is where you'll need your calculator handy when you're doing these problems for both the test and for, your web assign. We need to do the natural log of 25 divided by 6, which I got 1.427 something for that. Then we want to divide that by the 0.06. So that's going to round out to about 23 let's go to one decimal, 0.8. And this is in years. So, and on the one we did in class, we found the actual year, like calendar year, and that's because they gave us a starting point. They didn't give us any years here. We're just approximating how many years this will take. So this is a perfectly acceptable format for that answer. Okay, so that was the only one left in 5.4. We're going to switch over to 5.5 and 5.6. And remember, I'm going to highlight kind of these again or put something next to them. We learned, actually, I'll just have to draw it. We learned that really important are these three properties here for condensing and expanding logarithms. And then we also had a change of base formula a little further down that was also really important. So just starring those for us so we know that we need them. We're going to practice doing some more splitting logs up and putting them back together because we skipped over some of the easier ones on that section, and that'll help drive that home. We have a couple change of base problems I want to do. And then we also want to do some more solving problems. I believe we had some solving log equations that were not in my video that I already had. So let's just go back to these. We're expressing this in terms of x, y, z, or w, all to the first power. So that means every single argument that we write at the end should only have a single variable to the first power. So if you look at this first log base 3 here, it's been connected by multiplication. There's 3 variables connected inside. And remember, we learned that multiplication separates into the same log base, but with addition between the logs. That has that direct relationship to the exponent property where you multiply same base, which means you add the exponents. So multiplying inside an argument, we add the logs. Okay. And that's as far as we need to go on this one, because we split all three of these up into their own individual log, because multiplication turns into addition, and each one has an x, y, or z to the first power. So notice this one's a little bit easier than what we did in class. Let's look at B. This has multiplication on top and division. We learned in class that we like to split the division first. So that's going to be log base 3 of the numerator, which I forgot to write the x. So xc. And then minus log base 3 of the denominator. We learned that multiplication splits into addition. So this first one is going to split into a log 3 of x plus a log 3 of z minus a log 3 of y. Notice each argument has the variable to the first power. And if you check these, we said, remember, any argument, the piece of the argument that came from the top will have a positive in front of the log. Any piece of an argument from a log that has a denominator piece, it'll have a minus in front of it. So that does make sense. Okay, this one kind of ties into the harder one we did do in D in class. So let's talk about this. This is one that it's not y to the first power yet. It's going to have to be converted to its rational form. This is log base 3 of y to the member 1 over 5, because it's a fifth root. Remember, radicals, it's the exponent inside divided by the root. That's how you convert it back to an exponent. So since this is not to the first power, we need to use that rule that says that power in an argument can be brought to the front as a coefficient. So this is 1/5 log base 3 of y now. And so these three individual ones kind of were the lead into the one we did in class. This has kind of a combination of everything. So let's look at, and if you need a recap on that one too, I'm going to be posting my recording from a previous semester on just the lecture notes like I always do. So you could go and watch that as well. Okay, so we did D in class. Again, we did the harder of all of them. So let's talk about using the properties to put logs back together into a single log. So we see that this is separated by a plus, and they both have log base 4. So we're allowed to write this as one log if we multiply the arguments. So you can put them in any order you want. I like to do it alphabetical. So 3z times x is 3xz. That is now a single logarithm. Notice still both log base 4, but there's a minus between them. So that means when we connect them, the x is in the numerator and the 7y is in the denominator. So its subtraction turns into division. This is kind of the opposite of the last one we did in that previous one. This has a power or a coefficient in front, which we know is a power on our argument using the power rules. That's log base 4 of w to the 1/3. And again, I would be okay with that if you wrote it in a class like test on a paper pencil test, but WebAssign might want you to turn that back into the cubed root of w to the first, but we don't necessarily have to write the first. Okay, so again, these three kind of have pieces of each property, and this one was kind of a combination. We did A in class. So I wanted to solve some more equations, just showing you how these properties are really useful for us. So if you notice on the left side of this B, we have a minus between these two log base 10s. So we're going to write that as one log, still base 10. Remember, the top is the argument that had the positive log. The bottom argument part is the one that had the negative in front of its log. So it turns into division. On the other side, we have a coefficient in front. We need to put that back up as a power. So that's going to be log of 4 squared. Again, we have two logs that are the same base on each side. So that's the case 1 we talked about in section 5.4. So we set the arguments equal to each other. And we can go ahead and say that 4 squared is 16. If you want to throw it over 1, you can. This is a proportion, so we can cross multiply. So x plus 2 equals 16x. Subtract over that 1x, that would be a 15x over here. And we want to solve for x, so we have to divide by 15. Now the big part we talked about in class in section 5.4 and again when we did A is that all arguments of logs have to be greater than 0. The argument is the piece right after the log base, which here, remember, the base is hidden as 10. So each of these original parts have to stay greater than 0. So we need to make sure that our answer keeps x plus 2 greater than 0, x greater than 0, and the last argument was a 4, which is naturally greater than 0. So if we plug in 2/15 for each of these, we need to check off that that makes sense. 2/15 plus 2 is definitely positive. That's okay. 2/15 by itself is positive. So again, this solution works just fine. So notice we were able to solve a much more complicated looking equation by using our log properties to condense, and then using the case 1 scenario, that a log of the same base on each side, you set the arguments equal. The big thing to remember with all log equations is you have to solve the equation and then check the solutions. You have to make sure the arguments of your log stay greater than 0. So let's try a couple more of these that I had listed here. So this one has a plus between the two natural logs, same base, base E. So we can multiply the two arguments together, and I'll distribute that in just a minute. This has a number in front, so we can put that back up as a power so that our log is now written correctly as log on each side. I would go ahead and maybe work that out another step before going to solve it. So that's x squared plus 6x on this side. This is the square root. Remember, 9 to the 1/2 is a square root of 9 to the 1st. Remember, that's the 1/2 turns into the radical part. So that's a 3. Okay, so we set these equal. X squared plus 6x equals 3. Move everything over since this is quadratic. Unfortunately, this does not factor. There's no factors of 3 that are different sign that are going to make 6. So we have to use quadratic formula to solve it. So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. This is negative 6 plus or minus the square root of 36 plus 12 all over 2. That's negative 6 plus or minus the square root of 48 over 2. 48 has a perfect square in it, actually 2. 4 goes into it, but a bigger perfect square of 16 goes into it. 16 times 3. So that's 4 on the square root of 3 all over 2. So I think I have two solutions here. And if I reduce this by dividing everything by 2, of negative 3 plus or minus the square root, or 2 on the square root of 3. Let me write that correctly. So remember, we would split that into two solutions, a negative 3 minus a 2 square root of 3, and a negative 3 plus a 2 square root of 3. So the question becomes, well, how do you check these? Because we said we have to do a check on all of these. So the argument needs to stay greater than 0. The arguments on our log were x plus 6, and the 9. So x needs to be greater than 0, x plus 6 needs to be greater than 0, and 9. 9 is always greater than 0, so that part checks out. So how do I check these big old radicals? Well, in this situation, this would be a place where it'd be okay to get a decimal approximation for checking. So I'm going to work out these on my calculator and tell you what I get for each answer by just typing it in. So we're doing square root of 3 times a negative 2, and then that's got a minus 3 in front. So minus 3. I'm getting negative 6.46 for this one, approximately. Okay, now that wouldn't be how I would circle my final answer, but that will help me check it. And for the other one, it's square root of 3 times a positive 2 and minus a 3. I get 0.46. So the question is, if I plug 0.46 into both of these, because I believe that one's going to work, that's greater than 0. 0.46 plus 6 is definitely greater than 0. This one works out. So I can go ahead and circle the one that has the plus between them. I'm more worried about the negative one, and that fails right away. Negative 6.46 is not greater than 0. It's also not going to make this greater than 0, but as soon as it fails one of them, it's out. So this guy right here does not work. So just one solution. Now, I told you this was a good one to see for kind of like test level. We would probably give you one that's factorable though. I like to throw in at least one non-factorable just so you see how the quadratic stuff still plays out sometimes. And then it may be a little tricky to check those because you have to, work with those square roots. So just wanted you to see one that had, something non-factorable, but typically we would give you something maybe this level, but possibly that, is nicer and factors, and you can check the answers a little quicker. So let's look at D. On D, we need to definitely combine these. So we're going to end up multiplying those arguments together because it's got addition between the two logs. So it doesn't matter which one you write first. So I always like to write the monomial first. We're still multiplying them together. This is not a log over here. No place to put this. This is just a 2. I'll go ahead and distribute inside here. That's x squared plus 5x. And then this equals 2. So this is the case 2 type that we learned about in class today. There's a log on this side, but not on this side. So when you're dealing with this, the only possible way to solve it is to convert it to its exponential form. And just because all the stuff's blue and it's kind of running together, I'm going to change colors. So this will be 6 squared equals that x squared plus 5x. Base to the exponent equals the argument. So that's 36 equals x squared plus 5x. Again, a quadratic, so I'll move that over. I believe I was nicer this time though, and I gave you a factorable one. So that is an x plus 9 and an x minus 4. Multiplies to negative 36, adds to 5. So either my solution could possibly be negative 9 or 4 or possibly both or neither. We're going to check. So I need to know, are my arguments staying greater than 0? So my argument this time, it was an x plus 5 and an x. There is no argument on the right side of this one because there's no log. So I need to check if x plus 5 is greater than 0. When it's a negative 9, that's already false. So this guy's out. Don't even have to check it in the other part if it already fails. And then I'll check 4 plus 5 greater than 0. Yep, that's good. And for x greater than 0, 4 is definitely greater than 0. So 4 passes both tests. So this one had a single solution and an extraneous solution. Okay, so on the pre-made notes that I already had videotaped, I had done these two and this one, and I had left this one because I'd already done it in class. That video is sufficient, I think, to explain these because it's just showing you how to solve this or use change of base. And we actually, I do want to go over it again, at least this part right here. We learned to convert this to a log before, but now that you know about the case 1 type of equation, if you take a common log or the natural log of both sides of an equation, and that is allowed as long as you do it to both sides and the base is the same, that allows us to use that new property of pulling exponents to the front. So that is why we can get away with not always having to convert to log form by using the steps of log, base, argument equals exponent. If you are able to take a log of both sides of an exponential equation, you can bring powers to the front. You can try to isolate for x. So notice I'll solve this by finishing it and dividing that over. Now, and then I went through on the video and talked about how you type that in on your calculator and you get log 3 divided by log 4. And that comes out to approximately 0.79 to 2 decimal places. Also on that video, pay close attention because I talk about how this is actually called the exact solution and this is called the approximation. So you have to read to see what they're looking for. Sometimes they may want both. Now, same idea here. This is that change of base formula. So I'll do the one that was already kind of pre-done. When you have change of base, so notice we don't have a base 2 on our calculator. So we can change it to any base we want, whether it be natural log or log base 10. Why use something weird if you've got a button on your calculator? So as long as these are the same, you can do either log or natural log, okay? We always use the argument from the original as the argument on the top, the base of the original as the argument on the bottom. So this would be the exact form. Then if we wanted to approximate that, we type it in on our calculator, which they did ask for the estimate here. So natural log of 20 divided by natural log of 2. Type that on my calculator. That's about 4.32. Okay. So that's that approximate. That's what they wanted. Now, I do want to point out one other thing about like part 4, because there's a question on your review for your test. It may not have these exact numbers, but it's set up like this. It has something like this. So 5, 3 to the 6x equals 20. This is very similar to A. There's just one extra step that needs to be done first. If you are trying to solve for an exponent, you need to isolate that base first. So the first step on these, and we've talked about this a lot, that isolation technique, is you need to divide both sides by 5. So that would be 3 to the 6x equals 4. Now it's very similar to A. We're going to take the log of both sides so that we can pull that power to the front as a coefficient. That's how we get it out of the exponent. So then we pull the 6x to the front. That'd be 6x log of 3 equals log of 4. Again, just using our property of the exponents on a log in the argument. And then we divide not only by log 3, but also by 6. You have to divide everything that's not x to the other side. So this would be the exact right here, if they ask for the exact. And then we want the approximate, we would type that into our calculator. Now you might have to be careful. Anytime you have more than one log statement on the bottom, or if you've got coefficients and a log, you could actually put that in and make that 3 to the 6th and get a number. That would also be okay, because remember, you can move a number in front of a log up as a power on the argument. You don't necessarily have to do that if you can evaluate it without doing that. But we would need to do log of 4. And sometimes I tell people, put the whole denominator in a parentheses if you're not sure if you're typing it in correct. That just saves it so that the calculator knows to divide by all of it. So I would then probably type parentheses 6 times log 3, close my parentheses, and then hit enter. So I get about 0.21 for that if I wanted the approximate. So just be aware, if we give you that one on the test, which there is a similar one like in the examples of the review, it looks very much like the one we did here, but you do have to isolate that base first, okay? Part 6 is on the video I already posted right underneath this one. All right, so I want to do part A, I do on the video that I posted earlier today. And part B was already worked out, but I'd like to do it here since we didn't get to talk about this one. So when we look at this, we are looking at a problem where not only do the bases not match, and we can't make them match because I can only write 4 as 2 squared. That's the only other way to write it. 3 is not written any other way. There's no other way to make it a smaller base than itself. It's a little small prime number. But the problem here is that this is a little harder than the one I just did because there are x's in both exponents. So you can't really convert this to log form by like saying log blank blank equals blank, like when we were doing the 3 blanks. This is a type where because there's x's on both sides, we have to take the log of both sides to get those out of the powers. So the technique we use for these is always to take the log of both sides of my equation. We're going to write that. And I usually just use log base 10 because my calculator can calculate that later if I want. And then notice that I have right here, I'm going to highlight underneath this with blue. These are exponents. So these can come to the front using that log power rule. So this would then be 2 minus 3x. I'm putting it in parentheses because it's a binomial, times log of 3 equals 2x plus 1 times log of 4. Okay, so that's using the power in an argument can come to the front as a coefficient. We want to distribute these because we still have to somehow get the x's all on the same side. So this is just like a number. Log 3 is a number. So we're going to distribute it to both of these. That ends up being 2 log 3 minus 3x log 3. You can't multiply the 3 times the 3. Remember that's outside of a log, and that's right here, and this is inside of a log. So we're just writing them side by side. This would be 2x times log 4. And then we have 1 times log 4 would just be log 4. Okay, so now that we've got that done, I'm going to use the purpley color. Notice this term and this term both have the letter x. So our goal will be to get them on the same side together and anything that doesn't have x to go on the other side. So I like having everything positive with my log. It's personal preference. You don't have to. So I'm actually going to add the 3x log 3 to the right, and I'm going to subtract the log 4 over. As long as you do your operations correctly, it doesn't matter which way you move them, our fractions should still equal the same decimal in the end. So I'm going to subtract the log 4 over to this side. On this side, I'll have the 2x log 4 that was already here, and I'm adding the 3x log 3. Okay. This whole idea of putting the x's on the same side is because now we can factor that out front as a GCF in front of this binomial. So I'm going to keep writing this. This is 2 log 3 minus log 4 equals x parentheses 2 times log 4 plus 3 times log 3. Now, and I talk about this in my video for part A. Technically, at this point, if you just wanted to divide this binomial in this parentheses over to the other side, that is an exact answer, and that would be fine. The only thing is when you go to get the approximate, because it asks you for both in the directions, it'll say a 2 decimal approximation. That's a lot to type in, and you really do need parentheses around the entire numerator and the entire denominator to get your calculator to behave correctly. So I propose, and this is just how I like to do it because it makes the answer a little more compact, I look for any powers that can be put back in the logs. Like these coefficients in front of these logs can be put back in, remember, as powers. That will make this a little less messy. So this would then be log of 3 squared is 9, right? 3 to the second. There's no power to put back in front of this one. We just don't worry about the minus right now. We'll talk about that in a second. I have my x. Okay, so this will be 4 squared when I put it back in. So that's 16. That'll be 3 to the third, or 3 cubed. So that's 27. Notice that's still in the parentheses. And I can go one more step. Again, this makes typing it into the calculator and getting the decimal easier than just dividing this over and getting the answer as a big fraction. Anytime you see subtraction between two same base logs, that is truly division. So 9 divided by 4. Anytime we see addition between two logs, that is multiplication. So I need to work out that on my calculator. 16 times 27 is 432. So notice, if you use your properties, you get down to a single log on each side, and we just need to divide by the one that's beside our x. So I'll write both answers in just a second so you can see the two different exact versions. So acceptable versions of the exact answer, you could have just taken this point if you were just ready to be done and taken the left side, which was all of this, and divided it by the right part over here, which was a binomial as well. That's a 4, by the way. 2 log 4 plus 3 log 3. That is one way, and it is acceptable, okay? We don't sneer at that. It's just harder to type this all in your calculator. If you simplified everything down, you would have gotten a reduced log of 9 over 4 divided by a log of 432. That is also acceptable, okay? Technically, log 9 minus log 4 divided by log 16 plus log 27 is also acceptable. You just have to get x by itself, and it's really up to you. We're not nitpicky with students on this about how compact your logs become, how condensed they become. We just want to know that you can solve for the x and get everything out of the exponents. So just be aware, I would accept either of these or even that middle step as long as you get x by itself. Now, I will say the second version I gave, or this version right here, the one that only has one log on top and one log on bottom, that's a lot easier to evaluate in a calculator when you go to do the decimal. You just do log of 9/4 divided by log of 432, and that comes out to 0.13 for the approximate. So these are both exacts, right here and here. This is the approximate, because we actually used our calculator to simplify and estimate. All right, so I had on the video both 8 and 9 were on there, so make sure you watch the second video in the series. I don't want to overkill it on making you watch the same thing twice. I am going to make a separate video in just a few minutes that has the section 5.5 and 5.6 stuff that's on the version B of the review. I will probably post that under an announcement, whereas I'm posting all of this under week 7. So just be looking for that announcement that has that video as well. All right,